Okay, so this is Algebra 2, Lesson 7-5. We're going to start off with a little vocabulary this time, some different words that we're going to use, and you need to be able to distinguish between them so you can solve the problems correctly. So first of all, a simple event is mostly the probability that we've been finding is an event that describes a single outcome. So the probability of rolling a 3 on a dice, or the probability of being late given that you're on route C, or any of those other probabilities. That's still a single outcome event. A compound event is an event made up of two or more simple events. So we're going to look at those for the rest of this lesson. And when you have a compound event, it can either be mutually exclusive or inclusive. If it's mutually exclusive, the two events cannot occur at the same time. For example, if you roll a dice and then flip a coin, you can't get the same result twice. If you want to get an even number and a 1, well, those are completely separate categories. They don't overlap, so they are mutually exclusive. I can get an even and or a 1. Sorry, my English has to be correct in order for that to make sense. So I can get an even or a 1, and so those two requests are mutually exclusive. If I wanted to get an even or a 2, then those are inclusive because those overlap, because 2 is an even number. So hopefully that is understandable a little bit. You can also look up further definitions of those words if you want to, but we're going to do some examples here that hopefully will help explain them. So the probability of two inclusive, we're going to start with inclusive, the bottom one of those definitions. So these are going to be events that have some overlap happening. So the two inclusive events means the sum of their individual probabilities minus the probability of both occurring. So this is a new symbol probably for you. It means or, basically. So we want the probability of getting A or B here. And in order to do that, we need to find the probability of getting A, the probability of getting B. We can add those up, except for there's a problem because we may have double counted because it's in both, so we have to subtract that off. So here's an example. We're just going to roll a dice. So when you roll a dice, you can go 1, 2, 3, 4, 5, 6, right? So I'm going to use some colors here. What's the probability of getting a 5? Well, there's only one 5 there, so that's 1 out of 6 is my probability of getting a 5. What's the probability of getting an odd? 1, 3, and 5 are odd. So if I add this up, that doesn't make sense because here's the problem. I just double counted the 5. So then what I have to do is subtract off, that's this part right here. I need to subtract off that I have a odd 5. So there is one way in terms of probability to get an odd and a 5 at the same time. So I have to take that back off on the end. So basically you find each individual probability, but you also need to remember to subtract when they are overlapping. So you can also kind of do the circling thing. So if you just look at this, how many things did I circle or square? I circled 3 of them out of 6. And if you add this up, you get 3 out of 6, which is 1/2 or 0.5. And that is our probability for this problem. All right, let's try that again. We're still doing a dice, so here's my numbers. Let's do probability of getting an even. Circle, circle, circle the even ones. The probability of it being a factor of 6. What numbers go into 6? 1, 2, 3, and 6. So one thing I like to do is just look at this, and I know that the answer is going to be 5/6, but I'm going to show you how we got there. So let's go back to the probability of it being even was 3 out of 6. The probability of it being a factor of 6, there were 4 out of 6. But how many even factors of 6 are there? 2. So I have to subtract those. So you add the first 2 and subtract the third one. If you add this up, you get 5/6, which is correct. You can also write that as a decimal, 0.83 repeating. All right, and that confirms my little visual here of seeing that the answer should be 5/6. But this would be showing your work and showing that you're showing me the probability of A, the probability of B, minus the probability of both. All right, what if they're not inclusive? So if there isn't that overlap, guess what? It makes life a whole lot easier. If there is no overlap, for example, if I wanted to know the probability of getting a 1 and an even, that is not possible because 1 is not even. So the probability would be 0. It is impossible. So if A and B are mutually exclusive, the and part would be 0. So I can revert back to that formula I was just using, but this part is just 0. So really, this is much easier. All I need to do is find their individual probabilities and add them up. So what's the probability of getting a 5? There's one way on a dice. What's the probability of getting a 4? There's only one way on a dice. So, and I can't get a 5 and a 4 at the same time. I can only get one outcome when I roll the dice. So all I have to do is add these up. I don't have to worry about subtracting and double counting and all that stuff. So 1/3 or 0.3 repeating. There we go. Let's do another one. Probability of even. How many even numbers are there on a dice? 3 out of 6. And how many 3s? And then you just have to check, is 3 an even number? Is it in this list and in this list? No, it is not. So this is a plus. We are doing ands and ors, so we add 2/3, which is 0.6 repeating. And there we go. All right. Next up, we have some examples to just try this out a little bit, because when it's not staring you in the face, it's a little bit harder to figure out. So of 3,510 drivers surveyed, let's organize our data a little bit. We got drivers, we have male, and we have colorblind. And so we have male, female, and colorblind and not colorblind. Let's make a table, kind of adding up all these numbers. So let's go male, female, colorblind, not colorblind. So of the drivers, 1950 were male. So I know this total is 1950. 103 were colorblind total. Only 6 of the colorblind drivers were female. So right here, this 6 is colorblind females. Right now, I can fill in this other box, which means I could also fill in this other box. So let's do a little subtraction there. Subtract those, that leaves 97 colorblind males. And if I subtract the colorblind ones from the total number of males, I get 1853. Total, I also have a total number of drivers, so I can fill in this box with 1554. Not sure if we're going to need that one to answer the question, but we fill in the table anyway, and then we can answer the question. So what is the question? What's the probability that a driver was male or colorblind? Okay, so let's figure this out. What's the probability that they were male? Well, how many were male? 1950 out of the total, 3510. How many were colorblind? Colorblind is 103 out of the total. But we have a problem because we double counted the colorblind males. They were in this number that we added for the first problem and this number. So since we double counted them, we have to subtract off that 97 out of the total. So the bottom number is going to stay the same every time. Add and subtract that, and you get 1956 over 3510. And divide that, and you get 0.557 for your percent. All right, let's take a look at another example. But let me just give you a hint that drawing this table is really helpful. And one other way that can help is a Venn diagram, if you've done Venn diagrams. So we can have males, and we can have colorblind, and we can have, there are 97 colorblind males. There are 6 people that are colorblind that are not males. There are 1853 males that are not colorblind, and you can basically answer this question the same way. You just need the totals also. So the table's actually a little nicer, but some people like Venn diagrams. All right, one more example here. There are 5 students in a book club. Each student randomly chooses a book from a list of 10 titles. What's the probability that at least 2 students in the group choose the same book? So this is a little trick you can do. If I wanted to know that at least 2 people chose the same book. I would have to figure out the probability that 2 people did, that 3 people did, that 4 people did, that 5, 6, 7, 8, 9, 10. I would have to find out all of those probabilities and add them up, and that would be a lot. So it's a lot easier to figure out how many people did not choose the same book. So if we take the probability, if I want to find the probability that at least 2 students chose the same book, I could find the probability that everybody chose different books and just subtract that from 1, because these should be complementary probabilities. So they are the complement of each other, so we can just subtract it. So this is much easier to find than all of the individual 2 people and 3 people have the same book. So let's start finding the probability that they all chose different books. Well, we have 10 books and we're choosing 5 of them. And so that is basically 10 times 9 times 8 times 7 times 6 times, 1, 2, 3, 4, 5. And they would all be different because there's 10 for the first person. And then in order for it to be different, there's only 9 left for the next person. So this is 3024.3024 ways to choose it. And then, and that's how many ways, because there are 10, sorry, 30240. I did that wrong. There we go. The reason I put the point there is because to turn it into a probability, we need to know how many different options there were. Well, there were 10 options every single time. 10 times 10 times 10 times 10 times 10 for the 5 different ones. So it's a 1, 2, 3, 4, 5, a 10 with 5. So that's where the decimal came from. 0.3024 is the probability. Now that is the probability that they all chose different. So for my final answer, I just have to do 1 minus that number. So the probability is 0.6976. That would be the probability that at least 2 chose the same book. And that is the end of lesson 7.5, and that's what we're doing for chapter 7.